All right, well, thank you very much for the invitation and for the introduction. So it's a great pleasure to be back here. So as you just heard, I was an undergraduate and a graduate student here in 1990 onwards. It's always great fun to come back and see how things are going here. And every time I come back, there's a new building somewhere on this site. It's very impressive to see what's going on. So today I'm going to talk about supernovae with new facilities, and I'm going to talk mostly from a cosmology point of view. And I will be talking a bit about Euclid towards the end of the talk. And hopefully you've seen the nice press release a couple of days ago with these beautiful new images that have come out, and this is one of them. Let me just see if I can get this pointer going. There we go. So this is an image of the Perseus cluster, which is one of the press release images that Euclid released. So I will come back to this later, although a bit of a spoiler alert, I can't actually say really anything beyond what was released in the public data release, but I will be able to tell you about what the prospects are for Euclid towards the end. So I'm going to give a bit of introduction to the cosmology side of supernova searches. And of course, most of you will be aware of this huge mystery in physics, the whole issue of the accelerating expansion of the universe and what might be causing it. So we know, and mostly from supernovae, that the expansion of the universe is accelerating, but we really don't know why. And this term dark energy was introduced just to cover whatever it is that's causing the acceleration. So if you look at the history of the universe in this nice graphic from Discover magazine, starting with the Big Bang down here, as you would expect, the universe's expansion started to slow down because of gravitational attraction of the matter in the universe. But then sometime around, not too distant in the past, the expansion started to accelerate. And the reason behind that is really still not understood. So what I was going to do is give a little bit of background about the supernova technique, which I'm sure most of you are familiar with, and then I'm going to bring us up to date with supernova surveys and then where we're going in the future. So the sort of basis of all this is about how you go about measuring the acceleration of the universe, is that you need two main things. You need to know the size of the universe at different times, and you're essentially trying to get the second derivative of that size with respect to time. And so that is equivalent to measuring the scale factor of the universe, which you can get extremely directly just from redshift, because 1 plus z tells you the scale factor change between the time light left the object you're looking at and now. So that's the size component that we're trying to measure, but the other is the time, so if you like, the light travel time to the objects you're observing, and that's much harder. And so for that, you need to know something about the distance to these objects, which of course is one of the hardest things to do in astronomy, is measure how far things are away from us. So it's that distance aspect that we spend most of our time worrying about, and that's where the supernovae come in. So supernovae, the type 1a supernovae, are very good distance indicators. They're not perfect. There's quite a lot of scatter, particularly before you make any corrections, but there are ways to make type 1a supernovae very well standardized and excellent distance indicators. So to be able to measure this sort of acceleration effect, we need to find supernovae at different look-back times in the universe, different redshifts. So the way we do that is typically to, I'll skip, this is just linking two images together, which is nicely shown, an example from the high redshift supernova team where an object appears here, and I'm afraid that's about as spectacular as they get in these distant supernova searches. But mostly it's done by registering and subtracting images. So you have a template image, a new image, and you subtract the two after carefully registering them and getting their flux scales the same. And that gives you a candidate supernova object, but at that point you don't know what it is. It could be a real supernova, it could be a supernova of various different types, or it could be something completely different, even an asteroid moving into the field and moving out again. And so at that point, quite a lot of follow-up is needed. So one of the big components of these supernova searches has been collecting all that follow-up observations. And so I'm going to go through the components that we need, because this really feeds into how we design the next generation of surveys. So the things you need to do supernova cosmology is obviously you need to find the candidates that I've just briefly outlined. But then you need to know the type. So you need to be absolutely sure it's a type 1a supernova. And the way we typically did that, at least in the past, historically, is to take a spectrum and identify well-known spectral features. And in particular, this little dip here is from silicon, which is one of the defining features of the type 1a class. So you'd need to get a spectrum for that. You need a redshift to get the scale of the universe at the time. So that we typically get from the host galaxy of the supernova, because that would typically have narrower lines than the supernova itself, which has these broad features. So we use the narrow features in the host galaxy spectrum to get a redshift, and sometimes those two are blended together, and in fact that's the case in this one. You can actually see the broad supernova features on top of the narrow host galaxy features. And then you need the distance, which you get from measuring the peak brightness of the light curve. So this is an example light curve of a supernova rising and falling, and it's that you then fit a template to that and read off the peak magnitude. And then there are corrections we do to that as well, which I won't probably go into much. So then you've got the distance, and it's those three things that they're the absolute minimum that you need to be able to do cosmology, and that's quite a lot of observing time already. So you can see that to get this sort of project going in the beginning, it was actually quite hard work to convince telescope time allocation committees that it was worth investing all this follow-up observing time when the technique wasn't really proven. So what I thought I'd do is just go right back to the beginning about the motivation for these surveys, and then bring us up to date quite quickly with where they are now. So originally, the idea for these supernova surveys was to try and measure the scale factor of the universe with time, but I'll just show you the sort of scenarios that were kind of in play at the time. So at the time when these surveys were starting out in the early 90s, it was assumed that matter was certainly the dominant component of the universe, if not the only component. And in that scenario, there's really only three things that can happen to the scale factor of the universe with time, and I'm sure you've seen these sorts of plots before. One is if the matter density of the universe is greater than some critical value, the universe will collapse back on itself. If it's less than some critical value, the universe will continue to expand forever. And if the universe has exactly the right sort of critical mass, it will expand forever, but it will never actually collapse back. It will sort of asymptote to a fixed size. But in all three scenarios, because mass is the only component, the curvature is always downward. So you're always expecting some sort of deceleration of the expansion rate of the universe. And for various reasons, the omega matter equals 1, the critical value, was the one that was favoured at the time. That's partly because of the theory of inflation, which predicts that the total energy density in the universe should be 1. And if matter is the only component, then that means that the energy density in matter must be 1. But there were problems with that even at the time, which were that the ages of the oldest stars were coming out older than the universe should be for this omega matter equals 1 scenario. And there were hints from galaxy counts and clustering measurements that didn't fit this picture either. So the Supernova Cosmology project set out to try and measure that deceleration and answer once and for all which of those scenarios the universe is really on. And so they set out to measure the cosmic deceleration. And this is a nice picture from 1991 of some of the key players in that team at the time. Saul Perlmutter here, who went on to win the Nobel Prize, and other members of the team. And they were using the the Isaac Newton telescope, and La Palma, the camera there, which Richard McMahon and Mike Irwin were also involved in this, to try and start off the supernova searching on a sort of larger scale. And I then joined in later on in about 1994. So using these sorts of cameras, they were able to come up with a batch approach to finding supernovae, where they could actually guarantee that they would find supernovae on a particular date, because they were surveying large enough areas of the sky that you could guarantee there are enough galaxies in those images. At least one of them would have a supernova in it. So that meant you could pre-arrange your follow-up time And they were able to build up quite a large sample that way and then produce this well-known result, which this is a Hubble diagram now of these distant supernovae that they found. There are about 40 of them on the same Hubble diagram as a group of brighter nearby supernovae from the literature. So what's plotted here is the peak magnitude of the supernovae in the B band against redshift, and the cosmological models are shown on top, and the second to bottom one is the case with omega matter of 1 and no other component in the universe. And you can see straight away that the data at high redshift are above that second line, meaning that they're fainter than you would expect for that model. So that was the main evidence that there's something else in the universe that is making objects at high redshift appear fainter than they should be, or than were expected. And that's this other component at the time was, well, one explanation was that could be the cosmological constant lambda. So if you put in different quantities of lambda, that has the effect of effectively sort of pushing the universe apart and makes the more distant objects fainter. And so from these sorts of results, you could tell that about 70% of the energy density of the universe has to be in that other component. And when you put those two things together, that implied that the expansion of the universe should be accelerating. So that was the big result at the time. And it was found about the same time as the Rees et al. Paper, the sort of competitive group, the High Z supernova team, found the same result. And that was what led then into 2011 to the Nobel Prize for Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae. But you'll notice that citation doesn't mention anything about the cause. It's just for the observation. So what's causing it? So if we go back to this sort of diagram, what's been found is that it's none of those previous scenarios, that the universe is actually, it had some deceleration early on, but later times it's actually accelerating. So could it be the cosmological constant explanation? Well, it could be, but the problems with that are the size of the effect. So any sort of natural explanation that involves the cosmological constant, it's referring to vacuum energy in the universe, and the sort of natural explanations for the level that should be at are about 120 orders of magnitude lower than the amount that's been found through the supernova measurements. That's the cosmological constant problem, and it's one of the biggest problems in terms of scale. 120 orders of magnitude is obviously a massive problem, and that's something that's still not really been explained. The alternatives are something like maybe there's an inflation-like expansion going on late in time. Could it be that our theory of gravity is wrong? There are, there's various models, obviously. And one way we can attack this from the observational point of view is to make better supernova surveys, but obviously there are also other techniques for measuring cosmological parameters like baryon acoustic oscillations and weak lensing measurements. But I'm going to focus on the supernova measurements and how we can progress that way of attacking this problem. So once we've sort of moved on from just the fact that there has to be another component, the next step really is to look at its nature. And the way we address that is to look at the equation of state parameter W, which is the ratio of pressure to density. So we're kind of adding another free parameter now. As the data get better, we're able to start constraining what the equation of state parameter should be. And for the special case where the cosmological constant is the dark energy, we would measure exactly -1 by definition everywhere and at all times. So if we see any deviation in that W number from -1, we would then have proved that dark energy is not the cosmological constant, which would be an enormous result. And this is where the focus has been since those original results. So I'm going to whiz through now to where we are, get up to speed where we are now. So after those initial 40 objects, some large supernova surveys filled in the Hubble diagram quite spectacularly. Now this one, which was in 2014, is a compilation of supernova surveys which went up to 740 supernovae, and it's beautifully fit by the same cosmological model, with lambda being the explanation for the dark energy component. And you can start plotting the equation of state parameter W against omega matter and constrain parts of this diagram. And the supernovae give you this sort of blue banana shape here, which isn't terribly well constrained, but when you then combine it with some other results, say from the cosmic microwave background, the combination shown in grey there gives you pretty good constraints on W. And once again, they're coming out very close to the -1, or actually consistent with the -1 number, the key number that means it's consistent with the dark energy being the cosmological constant, that W of -1 line. So with that data, the uncertainties on W were about 5% when combined with other techniques. And then moving on to where we are now, this is probably the most recent compilation from 2022. And here we've got 1,500 type 1a supernovae. This is now plotted on a log scale, so it looks a little bit different. But we get very similar results, but with smaller uncertainties. So now the uncertainties are down to about 3%, including systematic errors now, but still consistent with the W of -1 value. And I've just tried to put all of these results on the same axes here. It's a bit of a mess, but I've just sort of superimposed them, and you can see that they actually all agree. There's some that I haven't mentioned, like the TiDES results, Dark Energy Survey results are there as well. It's hard to see, but basically they do all agree between the supernova surveys. And they're all finding this average value of W of -1 with 3 to 6% uncertainty, which is consistent with the cosmological constant, but we still don't understand why. So what is that actually? We still can't understand the 120 orders of magnitude problem. So I'm going to come on to where we're going next with this and how we're going to narrow down those uncertainties even further and hopefully give the theoretical models less wiggle room. But one of the key things that's come up with all these during all these surveys is that the supernovae, as I mentioned right at the beginning, they're not perfect standard candles, and we've had to make corrections to their brightness based on their colours and the shape of their light curves. These things all seem to correlate with the peak brightness in various ways. But another important effect that's come up more recently is that the brightness of the supernovae depends on the host galaxies that they're in. And so this is one example of that sort of manifestation of that result. So this is now plotting the relative brightness of supernovae that have already been corrected for the standard things that we correct for, the light curve stretch, we call it, and the colour. And you plot that against the colour of the host galaxy at the position of the supernova. And there's a subtle effect that you can see that the bluer galaxies tend to have very slightly fainter supernovae. If you just divide the sample in two, draw a line through the middle and plot the average brightness, they're slightly fainter on this side than they are on this side. Those are the two black points there. So something to do with the host galaxy is being reflected in the brightness of the type 1a supernovae. And this has to be corrected because obviously as the host galaxy population evolves with redshift, that could mean, if you don't correct for this, that the type 1a supernovae peak brightness will evolve with redshift, and that's not good for a standard candle. So we have to make a correction for this, and that is now done routinely. It's often implemented as a step function, a bit like this here, but as a function of the mass, the stellar mass of the host galaxy. And that's done in an empirical way, as are the other corrections we make, without really understanding why, in this particular case, why the correlation comes up. So is it because it could be something to do with dust properties? That's probably one of the leading theories at the moment. There's some difference in the dust properties between different host galaxies. But I think what it does tell us is that in future, if we're going to do large supernova surveys in the future, we need to not only measure those three things I mentioned at the beginning, the redshift, peak brightness, and the other thing, the type of supernova, but we also need to study the host galaxies on a large scale. Right, so moving swiftly on, and I do have to be quick. Supernovae are important. They're a leading method for cosmology. We're at the level where statistical and systematic effects are comparable. And the next steps, we're going to need larger samples, control of systematic effects, because those two things are comparable. We're going to need to classify supernovae, measure their redshifts, get the distances, and study host galaxies. And the goals are testing whether W is exactly -1 everywhere and at all times. So, it's basically saying the same things. Is dark energy spatially uniform, and does it vary with time? And I'm going to skip this slide on the right because it takes too long to explain. So, the next generation surveys then. So, one of the big breakthroughs is going to be when the Rubin Observatory switches on. And this is going to deliver vast numbers of transients, really just because of its large camera, its ability to survey huge areas of the sky every night. And a probably quite conservative number here is that it will find something like 100,000 supernovae with well-measured light curves out to redshift around 1. So with a sample like that, you can imagine splitting the sample into subsets around the sky, or so you could test whether dark energy is the same in different directions. You could test supernova evolution by breaking the sample into different redshift bins, and you can do tests on systematic effects, like do you get the same results for supernovae in one type of host galaxy compared to another? So this is going to be really powerful. But how are we going to get all this information, the other information that we need? And the main thing is that the spectroscopic follow-up that you need to get the type and the redshift is going to be a real bottleneck. And that's where the TiDES survey comes in. So TiDES stands for Time Domain Extragalactic Survey, and it's a survey that's going to run on the foremost instrument, which is an optical spectrograph for the Vista telescope in Chile. Actually, let me start this little movie going. That may be more. There we go. So at the heart of foremost is this fiber positioner, the Isobel positioner. It has these spines that can be positioned to match objects on the sky, and this is the full focal plane here with about 2,400 fibers on it. So the idea is that foremost is going to do a survey of the whole southern sky over about 5 years, and because once Rubin Observatory is running, basically everywhere that foremost points on the sky, the Rubin Observatory will have found some live transients quite recently, within a day or two. And so we can point fibers onto those transients and get a spectrum. So that's the idea. The idea of TiDES is that we're not going to be driving the foremost telescope. We're just going to follow other surveys that foremost is doing. For example, there are several galaxy surveys involved. We'll just piggyback on those and get spectra of live transients whenever one happens to be in the field. And we'll also, if there happens to be a supernova host galaxy in the field, which used to have a supernova, but the supernova's faded, we'll get a redshift of that. So this whole thing is being planned out quite carefully now. The whole thing should be starting late 2024. And I'm going to talk a bit about what we expect to get out of this now. So this is the, quite old now, but roughly the footprint of the LSST, Legacy Survey of Space and Time, main survey from Rubin. And this is the footprint of foremost. Again, not the final one probably, but it gives you an idea of the very large overlap between the two surveys in their area. Of course, the difference is here that whereas Rubin will keep going back to the same fields over and over again, for most of foremost's survey, it will only visit once or twice each patch. But still, because of, as I mentioned, wherever foremost looks, Rubin will have generated supernovae. By the time you've added up 5 years of survey, you end up with some very large numbers. So this is a very nice animation by Chris Fromeyer at Southampton, showing how this will work based on realistic simulations of Rubin's survey strategy and foremost's. So the Rubin strategy is the one in this color scheme here, and the foremost pointings are in red. So this was without putting in any attempt to coordinate the two. It's just how the two surveys worked out by chance. And obviously they're going to be looking at roughly the same areas of sky because that's the part of sky that's going overhead. So even just letting them run independently, you end up with reasonably good overlap. So the TiDES live part of this, we call it, this is the part that is trying to get live transients. We're going to be trying to find type 1a supernovae, core collapse supernovae, or other types, But we won't know, of course, what they are. What we're going to do is basically a blind survey of everything that Rubin finds that's brighter than 22.5 magnitude. And the reason for that is just because we have enough fibers to do everything, and it's probably safer to just do a blind survey than try and select things based on early light curves. Otherwise, we run the risk of biasing our cosmological sample. So that's what we're going to do for the live supernovae. And then for the hosts, we're going to take redshifts of host galaxies of supernovae which have already faded, and that will be everything brighter than about 22nd magnitude. Or in special fields where Foremost does repeat observations, we'll get to about 24th magnitude. So that's just the deep drilling fields, which match Foremost's deep fields. So after about 5 years, we expect to end up with this sort of distribution of redshifts. There's a lot going on here, but the main group for this talk anyway is the type 1a supernovae in pink there, which will go out to about redshift 0.6. And we expect around 20,000 of them. And we'll be able to use, but we'll get lots of other types as well, and we'll be able to use them for lots of different things. We'll get the spectral classification of very large numbers of transients. So we'll be able to do things like transient demographics, rate measurements, their physical properties, because we'll have reasonably good spectra, and we can certainly trigger follow-up spectra in more detail. And we can use this sample as a training sample for photometric classification of the ones that we don't get spectra for. And I'm going to spend a bit of time on that later. And obviously what I'm particularly interested in is the selection of the type 1a sample for cosmology. And for that, we'll need the quite detailed LSST light curves to go with the spectra. So Chris Frohmeyer and Maria Vincenzi have done some nice simulations, sort of end-to-end, with the LSST survey and the Foremost survey superimposed. And this is the final, or one realization, given that the survey designs aren't final yet, but this is the sort of thing that we expect to get for the Hubble diagram. So after 5 years, we'll get about 35,000 live transients, of which about 20,000 will be type 1a. So they will have spectra and we'll be able to classify them. So those are the red points shown on the Hubble diagram here. Plus about 10,000 type 1a supernova host galaxies where we haven't got a spectrum of the supernova, but we have got the spectrum of the host galaxy and a nice light curve for the supernova. And we'll use photometric classification to confirm the type. And I'm going to come back to that a little bit later. And then there's a third component in green here, which I'm not going to talk about at all, really, but that's an AGN reverberation mapping experiment that is built into TiDES as well, and that will work mostly on AGN in the deep fields. So combined with those, with the supernovae on their own, actually not with the AGN, but we expect to get better than 2% measurement of W from this experiment, and that's because we'll have the well-calibrated light curves and all this spectroscopic confirmation. So there's quite a lot of things we can do with this sort of data, and I'm going to talk now about some of the things that, some of the recent work that we've been doing, mostly on simulations, obviously, and I'm going to focus mostly on what we've been doing in the group at Lancaster. I'll just mention, so the ones in starred here are the things I've either already mentioned or I will mention in a minute. But I'll just very briefly mention that my former student, John Carrick, did a nice bit of work showing how you can use the TiDES spectroscopic sample as a training sample in machine learning to classify the ones where we don't have spectra. Even though TiDES has quite a bright limit of 22.5 magnitude, which is a lot brighter than LSST will go, you can actually compensate for this biased training sample using data augmentation. And that he showed that very nicely, but I haven't really got time to go into that. So I've already mentioned the statistics of the transients and the cosmology simulations that Chris Frohmeyer and colleagues have done. I'm going to focus on some of these later things to do with how we can measure the host galaxy properties that we're going to need and what the implications of that are for doing the photometric classification, and then a little bit about the spectral classification of all these supernovae as well. So, first of all, the host galaxy properties. So I mentioned earlier that these correlations have been found between host galaxy properties and the brightness of type 1a supernovae, which is kind of important to understand and to be able to correct for. So there's a potential here, because we're getting nice spectra of all the host galaxies, not just photometry anymore. Can we actually improve some of these, at least the corrections that we make? So what we've tried to do was test this. I'll put all the bullets up here and just go through it very quickly. So the idea is we tested it with some spectra of known properties. We simulated the photometry you'd get from LSST and the spectrum you'd get from TiDES using assumptions that we'd have the 10-year depth for LSST, and we used the foremost exposure time calculator to calculate the real noise properties of the spectra. And then we fitted them as if we'd just received those spectra, put them through some SED fitting code called FAST. We chose this one because it can deal with photometry and spectroscopy simultaneously. And then we get out from that fits for the stellar mass, star formation rate, age, and various other properties of the galaxy. And then we compare the two to see how much better spectroscopy does than photometry, and compare with the original input, and quantify the improvement. So these are the sorts of results we've been getting. So unsurprisingly, when you add in extra information from the spectrum, you get a smaller uncertainty on these physical properties. And that's not something we really were surprised by, but the point is that we quantified it. So this is one example. This is the stellar mass of the galaxies, the simulated galaxies against their magnitude. And there's this very strong sort of correlation here. That's just because the FAST routine really just uses the brightness of the galaxy to estimate or get a first estimate of the mass. But what's interesting is the uncertainties, the error bars. So when we just put in the photometric points, you get this uncertainty in red here on the stellar masses. When you put in the spectrum information as well, you get smaller error bars. And then the diamonds are what you would, well, the filled diamond here is the input, where we know the values exactly because that's a simulated spectrum. And the open diamonds are extrapolated from that based on the brightness. So what you would hope is that you get smaller error bars for the spectroscopy and that they match those extrapolated target, and they do. So we can quantify that improvement, and then we can use that for various things. And one of the things we tried to do was to see whether, with better measurements of mass, how often can you, if you had a sample with sort of expected error bars on their mass, how often do they end up on the wrong side of the mass correction when you're doing this step correction? And it happens fairly often, but not enough to make a big difference. And what was tending to happen was that some objects, if their mass measurements were so large with the photometry, they'd end up on the wrong side, but then another object would compensate for that by also being on the wrong side of the correction, and you'd end up with, actually, it doesn't make much difference to the final answer on your measurement of W. So that was interesting, but it's a sort of null result. So the next thing we were interested in seeing was whether these physical parameters could help us with the classification. And there I think we found something a bit more interesting, and I'm going to come back to that in just a minute. I've just wanted to briefly mention that was a plot for measuring stellar mass. This is what happens when you look at the results for the age of galaxies. So again, plotted against magnitude, and 4 different redshift ranges tested here, 0.1, 0.3, 0.5, 0.7. And you can see here, in all scenarios, we see quite a lot better measurements when you put in the spectroscopy for the age. So this could be quite interesting if it turns out that age is one of the factors that is really driving this correlation with the supernova brightness. Then measuring the ages could be very interesting for this very large sample that we're going to get. Right, so I'm going to move on to the classification question. So we know that supernova occur at different rates. Different types of supernova appear in different types of galaxy with different rates. So in principle, if you know something about the type of galaxy, you might be able to learn about the classification of supernova just from the host galaxy properties. And certainly if you put that together with the light curve properties, we might be in a good position to classify supernova better. So that was a motivation for seeing how much this information is going to help us. So do these improved physical parameters help with photometric light curve classification if you don't have a spectrum of the supernova. So we decided to test this with a machine learning approach. And I should say now, this is done by my student, Jamie Domain, who's just writing up right now. He's used the supernova, which is a deep neural network classification method by Anais Muller. And what it does is it learns from a set of template light curves, which is what's shown here, multicolor light curves. It can then match it learns from a set where it knows the true classification and the light curve shape, and then you can apply that to a new set of data and it will try to classify the data based only on the light curves. So what we did is we ran this code on a set of simulations, the same ones that I showed for that simulated Hubble diagram, where we have these simulated light curves for every object. We know the true type of the supernova because that was put into the model. And these simulations also include some intrinsic correlations based on real correlations, and it's those that we can use to see how well this extra information is going to help with classification. So then, once we start with this basic version of supernova, which just classifies light curves, but then we can add in various host galaxy properties as extra training information, and we can put in things like the redshift, the stellar mass, and the star formation rate, which we can assume that we can sort of simulate that we've measured with TiDES, and see how well it does with that extra information. So that's what's shown here. And I think this is quite interesting. So what we've got here is different models, different amounts of information going into the training. And on the x-axis we've used the precision of the output as our sort of metric. So the precision is the true positive rate divided by the true positives plus false positives. So it's what, on the bottom there is everything that it thinks is classified as a type 1a supernova. And on the top is the ones that really are type 1a supernova. So it's 1 minus the contamination rate, if you like. So if we had a set of objects which the code says are type 1a supernovae, what fraction of them really are? So obviously you want to be on the right-hand side of this graph. So the first thing is, if you only give it light curve information, how well does it do? No host galaxy information at all, and it's already doing pretty well. So it's finding more than 96% pure sample. So that's already a very good start. If you add in a little bit more information and put in redshifts, but with quite large scatter, as you would expect from photometric redshifts, it improves this a little bit. But if you put in spectroscopic redshifts, so basically the known redshift without any error, you do much better. Well, significantly better. It's already pretty good, but it does better. So then that's just redshift. If you now start adding some host galaxy information in, the actual physical properties, some interesting things happen. So if you we tried adding in the photometric properties of the galaxies, and now I'm talking about the mass and the star formation rate, as determined from FAST, with the uncertainties that you would expect from FAST. It actually does worse when you assume those uncertainties just come from the photometric information. And that's quite a strange thing, because we're giving it more information and yet it's performing worse. And we think probably what's happening is that in quite a few cases, the photometric fits, the fits to the photometric data have such large uncertainties that sometimes it hits the limits of FAST's error range, and it's just basically adding noise. It's not really adding any real information for such a large number of the objects that it really doesn't help at all for the whole sample. But when we then convert to smaller scatter that you would expect from TiDES, it does much better again, and actually is better than just the spectroscopic redshifts alone. And then finally, the red point is with no uncertainties at all. So that's the best you can do with this particular sample. So I think that's quite encouraging. This is still preliminary results, but it does look as though we're going to be able to improve our photometric classification by including some information on the host galaxies that we get from the spectra, and I think that's really nice. Right, I really do have to speed up. I can skip this really quickly. So classification of transient spectra is something we're going to have to grapple with. We're going to get 35,000 spectra coming out in real time, and we've made a promise that we will deliver the classification and redshifts of these within 24 hours. So we're going to have to find some good code that will classify objects quickly. And we're doing some tests now to decide which codes to use. And my student Andrew Milligan has been doing quite a lot of work on this with Young-Lo Kim as well, who's a postdoc at Lancaster. And what he's been doing is working out the correct way to produce blended spectra, or simulated blended spectra from Foremost, using the exposure time calculator again, but now putting in not just the supernova object, but a bit of host galaxy light. So he's taking a bit of, this is the supernova, you work out how much light goes down a fiber aperture, and then do the same for a galaxy, assuming it's an extended profile. And he uses various assumptions that are in the simulations and puts them together into a spectrum. And then you can, with that massive sample of blended spectra, you can run them through various classification codes and see how well they do. And this is very preliminary, so I'm not really going to spend any time on this. But we've looked at the DASH code with and without redshift information, next generation superfit and SNID, which are well-known supernova classifying codes in the literature. And our idea now is to try and work out which perform best in which scenarios, and maybe we'll combine the three. We're not quite sure what's going to be the best option there, but we've got that underway. Right, okay, so the last thing I want to get onto briefly is Euclid, which is all very exciting, and as you will know, it was launched successfully in July. The key to Euclid is these wide field images that it has on board. It has a wide field optical imager and a near infrared instrument as well, both of which have a half square degree field of view. And the near infrared instrument can do imaging and spectroscopy. So Euclid's going to survey much of the extragalactic sky over a 6-year mission. I think I've got it. Yeah, okay. I'll come to the sky plot in a minute. So this is just showing one of the commissioning images that came out very early. That shows the field of view, which is about 0.7 degrees on a side. So the area is 0.5 square degrees. And you can see the detail of the image there, but there's much nicer images now. So that's the visible instrument, which is 36 CCDs making up this focal plane. And the near-infrared imager has 16 near-infrared detectors, all performing very nicely. And there's this GRISM spectroscopy mode as well, which will be taking spectra at different orientations, which will allow it to be able to separate out the overlaps of the spectra. So there's going to be a vast amount of data here. And this is the sky coverage of Euclid shown in green here. Again, this is one iteration of the survey design, and this has just recently been changed because of one of the problems with the stray light that was found to be entering Euclid reflected off from the sun of some component of Euclid. So they've had to redesign the whole survey with a very slightly different tilt to the sun, which has taken time and will slightly change the pattern. But general idea, it will be very similar to that. So transients in Euclid has had quite a history. And the basic problem is that Euclid was not designed to find transients. Its wide survey will basically visit each part of the sky once. And the only really interesting fields will be the deep fields that have repeat visits, but they have quite sparse time sampling. And that's shown in this paper by Cosmo and Sarah showed this for different deep fields, the timing of the observations. And so that's a 6-month gap for that particular field. So there are some intense periods and then some very big gaps, and it's really not ideal. There has been a study that showed if you could devote about 6 months of Euclid time to a dedicated transient survey, it would come out really well, and you'd be able to do supernovae right out to redshift 1.5. That's still a possibility, actually. If Euclid has time in its survey towards the end, that might still be a possibility. But for now, we're thinking about what could be done in the baseline survey. And here, I think it's important to remember that the near-infrared wide field survey really is unique. And so just with the baseline survey, which will operate both near-infrared and VIS instruments, we'll be able to do long-duration bright transients, well, and faint transients actually, but long duration is the key, that go beyond these gaps, So things like superluminous supernovae and pair instability supernovae, the very first supernovae at high redshift, could be detectable to very high redshift, around redshift 5, but with high uncertainty on their rates. And there is the potential for the first proper discovery if we're lucky. Might get lots of other transient types, well, we will. We'll be able to measure rates, including obscure transients, so things that are extincted heavily in the optical, we'll be able to see in the near infrared, and look at their environments over wide areas of the sky, and supernova cosmology, so that although Euclid won't get nice light curves on its own, it will be able to be used in combination with Rubin light curves, and it will get some live near-infrared photometry just by chance on the same objects that Rubin is observing. Oh, sorry, that's gone a bit wrong. So there's been a recent paper on this that predicts there should be thousands of these supernovae with a few near-infrared light curve points, which will help us constrain the effects of dust. And that could be really important for understanding this mass step correction. And we'll get high-quality imaging and photometry and near-infrared spectra of the host galaxies, which I think is particularly interesting. And that gives me an excuse to show some of the nice images that were shown at the press release. So this is a subset of the Perseus cluster field. So these are bright galaxies within the Perseus cluster. But just in the background, you can start to see how many galaxies there are, and that's just a small section. And if you zoom in even further, this was done with ESA Sky. So I'd highly recommend going to ESA Sky and exploring these images because they've got the full resolution images in there. So I've zoomed in a bit. This is about 2.1 by 1.5 arc minutes. And I've pulled up the low intensity scale so you can see some of the fainter objects. And they're just everywhere, these galaxies. So you can imagine wherever LSST finds a supernova, we'll be able to find the galaxy properties from images like this, at this sort of quality. We'll know their infrared colors, we'll know their morphologies from the optical, we'll be able to say where in the galaxy it exploded, is it in a spiral arm, and so on. So really exciting. Lots of prospects there, and spectroscopy as well. So I'm literally on I've got like 2 more slides to go on Euclid, which I want to cover. There's a new opportunity came up really late, which is that there's a field, the self-calibration field in Euclid, which is a 3-degree field, 3 square degrees, that's going to be observed repeatedly to do calibration tests. And that's a very good opportunity for transients. So it is being observed actually in the first 8 weeks, that's right now, about 6 times. So that's actually happening as I speak. And then once this PV phase, which is the performance verification phase, is finished, that field will be used as a checking field roughly monthly during the nominal mission. So I've called those short and long surveys because I'm going to show you a few predicted numbers in a minute for those 2 scenarios. So let me just pull that all up. So I think this is looking really interesting. So we think that just from that short survey in the PV phase, just in this self-cal field, we'll get about 25 supernovae, of which 6 will be at redshift 1, greater than 1. So there's a type 1a supernovae, and another 30 core collapse supernovae, of which 4 will be redshift above 1. And those will all have 3 detections at least. So that's 10 supernovae above redshift 1, just in a few weeks. That's really interesting and a great test, and will help us get the machinery going for supernova searches later in the survey. And then over the longer duration of, just from the self-cal field, we'll get over 500 supernovae at redshift 1, but they'll only have 1 detection because of this the large spacing, and potentially 10 superluminous supernovae, and depending on rates, 2 to 20 pair instability supernovae out to redshift 5. So this looks really interesting, and we're very excited about getting this started. Latest news, so now, as I said, I can't really say anything, I'm not supposed to, but what I think I can say that we know that Euclid is capable of finding transients, so you can read that into that what you like. The self-cal field search is underway. We've got 3 epochs already, and the first 2 were just on 1 subfield. The real issue is that because this data is being used to test all the pipeline, we're having to start from raw data in our analysis. So we don't have calibrated data. We're having real problems with the cosmic ray removal, the astrometry. These all turn out to be very difficult. And persistence in the near-infrared detectors has been quite a challenge as well. So it's hard, but it will get much easier as we all get more familiar with the data. And our expectation, as I showed you, is that this is going to be an excellent test case for getting the rates of transients, being able to do these large-scale detections in the infrared. And we'll be able to scale things up to the full deep fields, which will be about 40 square degrees, so more than 10 times the area, and potentially a dedicated survey later. So I'll wrap up there. So the summary is we're really at the limits of what we can do with current telescopes, but we've got this spectacular suite of new things coming with Euclid and foremost particularly, and the Rubin Observatory. So we'll get better statistics, better control of systematics, and we'll be able to extend, well, I haven't really talked about higher redshift at all, but that's going on as well. And we'll be able to test the properties of dark energy and hopefully get a precise value of W and check whether it's constant in time and space. And I'm going to stop there.